Hello students. In the previous class we have already started with the chapter chemical bonding, and we have discussed the ionic bond, covalent bond and dative bond in detail, and we have also discussed the properties of those types of bonds. Today we will discuss some other aspects of the chemical bond, and first we will start with the formal charge and its calculation. So formal charge means formal charge on an atom is the difference between the number of valence electrons in an isolated atom, that is the free atom. So the number of valence electrons on the free atom and the number of electrons which are assigned to that atom in a Lewis structure. So the difference between these two types of electrons is the formal charge. Let me show you. So this is the formula where formal charge of an atom in Lewis structure is equal to total number of valence electrons on the free atom, that is the central atom, minus half of the total number of shared electrons, that means the electrons which have been shared, minus total number of unshared valence electrons. So this unshared valence electrons is mainly in terms of the lone pair of electrons. So simply we can say that formal charge is equal to number of valence electrons minus half of number of shared electrons minus number of lone pair of electrons. Clear? Now let me show you how this formal charge is calculated on oxygen atom of ozone. See, this is the structure of ozone. On simplification we can draw this in this way. Here two lone pair of electrons are there. Two electron pairs are shared. Here one electron pair is shared with this one with three lone pair of electrons, and on this oxygen atom two lone pairs are there. So this is the simplified structure. Okay. Now if we want to calculate the formal charge on this central oxygen atom, so let's number it as 1. So formal charge on oxygen 1, it will be equal to, see, number of valence electrons on oxygen 6 minus half of number of shared pair of electrons. Now see, here how many electrons have been shared? 1, 2, 3, 4, 5, 6. 6 electrons have been shared. So half into 6, this part. Now for the number of lone pairs, here only 2 means lone pair is 1, but number of unshared valence electrons are 2. 2 electrons are not shared here. So it will be 2. Okay. So this will turn to be plus 1. Clear? Now if we want to calculate the formal charge on this oxygen atom, suppose this one is 2. So formal charge on oxygen 2, it will be, see, again the number of valence electron is 6 for oxygen atom, half of the number of shared electron pairs. Here 1, 2, 3, 4. 4 electron pairs means 4 number of electrons are shared, means 2 electron pairs are shared. So number of electrons that have been shared is 4, and number of electrons which are remaining as the unshared valence electrons are 4 here. These are the unshared electrons. So it will be minus 4. So this will turn to be ultimately 0. Okay. So the formal charge on this oxygen atom is 0. Now coming to this part, the third one. So the formal charge on O3, it is equal to, this one is again 6. Now half of, see, here only 2 electrons are shared. So the number of shared electrons are 2, and how many electrons are remaining as the unshared one? 1, 2, 3, 4, 5, 6. 6 electrons are not shared. So it will be minus 6. Clear? So here the formal charge is only minus 1. So in this way we will calculate the formal charge on the separate atoms of a particular compound using this formula, that formal charge is equal to number of valence electrons on the free atom minus half of the number of shared electrons minus the number of unshared electrons. Clear? Let's take another example. If we want to calculate the formal charge on chlorine atom of HClO4, how will we calculate? So this is the structure for HClO4 and we want to calculate the formal charge on chlorine atom here. So the formal charge on chlorine atom will be how much? First we need to calculate the number of valence electrons on the free chlorine atom, that is 7. Okay, then half of the number of shared electrons. So here 1, 2, 3, 4, 5, 6, 7, 8. 8 electrons are shared, and how many electrons are not shared? No electrons, means there is no remaining electrons which are not shared, so it will be 0. Okay, so this will turn to be only 3. So the formal charge on chlorine atom for this case is 3, that is plus 3. Okay, so in this way we can calculate the formal charge on the separate atoms in the combined state. Clear? See, the main advantage of the calculation of formal charges is to get the idea about the stability of the structures. There are many possible Lewis structures of a particular compound, right? So out of the different possible Lewis structures of the compounds, the structure which has the smallest formal charge on its atoms, it is connected with the lowest energy. That means the structure which has the least formal charge on its atoms, it has the lowest energy, and the substance which has the lowest energy is considered as the most stable compound, right? So in this way we get the advantage of the calculation of formal charge. Now, although octet rule is successful enough to explain the valencies of large number of elements, but it has some limitations. So now we will discuss the limitations of octet rule and the approach of valence bond theory. So let's start with the limitations of octet rule. There are many compounds whose stability could not be explained using the octet rule. Let's discuss one by one. So first we will discuss the formation of the compounds with electron deficient atoms. That means the compounds where some electron deficient atoms are connected. In those cases the octet rule is not applicable for their stability. See, according to the octet rule, the elements which belong to the group 1 or group 2 and group 13, they should not form the covalent bonds because they have less than 4 number of electrons in their valence shell. So they can never achieve the octet by mutual sharing, right? So according to octet rule, they have to transfer the electrons and then they have to gain the stability or achieve the octet. But some elements are there which form covalent bonds like LiCl. In case of lithium chloride, it is expected that lithium will donate 1 electron to chlorine and then the ionic bond will form. But this doesn't happen. What happens? In case of lithium, as the atomic radius is smaller and due to high nuclear charge, the valence electron cannot be transferred easily. So lithium undergoes the covalent bond formation. Okay. So in case of LiCl, this 1 electron of lithium is shared with the 1 unpaired electron of chlorine. So here one covalent bond, LiCl forms a covalent bond, and you can see here lithium atom has only 2 electrons here after sharing. Still the compound is stable. So according to octet rule, this compound is not stable and this compound cannot form. But actually this LiCl compound is stable one and there is the mutual sharing of electrons. Again we can take some other examples. In case of beryllium fluoride, BeF2. In case of BeF2, it is a linear structure. So here the fluorine atoms, they have 7 electrons in its valence shell. This fluorine also have 7 electrons in its valence shell, and this beryllium shares 2 electrons with the 2 separate fluorine atoms, and there is a covalent bond formation. Okay, so here also this beryllium, it has only 4 electrons in its outermost shell, and this is also not achieving the octet. Again in case of BCl3, boron trichloride, BCl3, so boron also shares 3 electrons with the with the 3 separate chlorine atoms. Okay, and in case of BCl3, the boron atom has only 6 electrons in its outermost shell after the sharing of electrons. So here also the octet is not achieved. Here only 4 electrons are there in its valence shell of the central metal atom or central atom. So here also the octet is not achieved, and in this case also only 6 electrons are there. That means in this case the compounds are electron deficient. Means the central atoms, they are the electron deficient atoms, and this is the limitation of octet rule, that despite being electron deficient, they are the stable compounds. That means octet is not achieved here, still the compounds are stable. The next case we can take the example of superoctet molecules. Okay, in case of some compounds like PCl5 or SF6 or IF7, these compounds, means in case of these compounds, the central metal atom have the, or central atom have the electrons, means the valence electrons are more than 8. So in this case also the octet rule is violated. Let's take the example of PCl5. In case of PCl5, the phosphorus has only 5 electrons in its valence shell. Okay, so let's draw it in this way. And rest of the chlorines are here. So here you can see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 electrons are there in the valence shell of phosphorus, which is impossible, right? How can one atom be stable by achieving more than 8 electrons? According to octet rule, it is not stable, right? But this PCl5 is a stable compound. So this is called the superoctet molecule. Clear? In case of SF6 also, one sulfur atom is connected with 6 fluoride ions, right? So in this case, 12 electrons are there in the valence shell of sulfur. This is the central atom. So around sulfur 12 electrons are there, which is also an example of superoctet molecule. Again, in case of IF7, iodine and fluorine, they get combined to form IF7, and in this case there are 14 electrons outside iodine, okay, which is also impossible because they are having more than 8 electrons in their valence shell, and this case is called the superoctet state. So these compounds are stable, but they are not following the octet rule. So this is another limitation of octet rule. Some other examples are also there, like in case of the formation of oxyfluoro compounds of xenon. As I have already said in the previous classes, that among the noble gases, only xenon and krypton mainly forms some of the compounds with the most electronegative elements like oxygen and fluorine. So in case of xenon, more than krypton, xenon is mostly known to form some of the compounds with oxygen and fluorine. Okay, this is because oxygen and fluorine have the highest electronegativity, so they have the tendency to attract the shared pair of electrons towards themselves. And xenon being means it has the greater atomic radius, so it's quite possible for oxygen and fluorine in combined state, they just form some of the compounds with xenon. Okay, so in this case also octet rule is not applicable for such formations. So in case of oxyfluoro compounds like XeF2 or XeF4, or we can take the example of XeOF2, XeOF4, etc. So for these cases octet rule is not applicable. Okay, again in some of the odd electron molecules, for the odd electron molecules also, this octet rule is not applicable. Now what is this odd electron molecule? See, in case of the NO or NO2, the structure of NO is one nitrogen atom gets doubly bonded with one oxygen atom with one lone pair of electrons and one lone electron on nitrogen and two lone pair of electrons on oxygen. So in this case there is odd number of electrons around some of the atoms. Like in this case there is odd number of electrons around nitrogen. Again in case of NO2, here the structure is in this way. And one double bonded oxygen, one plus charge, it is the electron deficient center and it is the electron rich center. This oxygen center is the electron rich center. So this exists in this way only. These two structures are the stable structures. So octet rule is not also applicable in these cases. So for the compounds like NO or NO2, octet rule is not applicable. Clear? Due to the formation of odd electron molecules. Again, octet rule could not explain the energy states or energy changes during the bond formation. So this is also a limitation, that the inability to predict the energy changes in case of the formation of the stable compounds. So this is another limitation of octet rule. So these are the main limitations of octet rule which led to further study of the formation of compounds or the chemical bonds. And after the failure of octet rule, the other theories like VSEPR theory or molecular orbital theory or valence bond theory were approached. So now we will discuss the valence bond theory. The approach of valence bond theory, that is VBT, it was developed by Hitler and London, and further it was improved by Pauling. Now this VBT is also called the orbital concept of bonding. Now to understand this theory, we need to take the example of the formation of hydrogen molecule, that is the diatomic hydrogen gas. And using this concept only, we will understand how the concept of orbital theory is introduced here. Okay, so let's start with the dissociation of hydrogen molecule. See, experimentally it is seen that when hydrogen gas is heated, that means this diatomic hydrogen in gaseous state, when this is heated at very high temperature, then it gets dissociated to form two separate hydrogen atoms in gaseous state, like this. Okay, and on heating, the energy which is required is near equal to 435.8 kilojoule. Okay, this much energy is required to break this bond between two hydrogen atoms and prepare the two separate hydrogen atom in gaseous state. So this equation tells us that 1 mole of hydrogen molecule, it needs near about this much quantity of energy to get dissociated to form two separate gaseous hydrogen atoms. Okay, so in other words, we can say that a molecule of hydrogen has lower energy than the hydrogen atoms. Clear? Now let's see how this lowering of energy occurs when the two hydrogen atoms become a hydrogen molecule. Clear? We know that the electronic configuration of hydrogen is 1s1. That means only one electron is present in the s orbital. So if we take these two separate hydrogen atoms, let's consider the first hydrogen atom as Ha, which contains the electron Ea. Okay, and for this one, if it is Hb, then the electron is Eb. Clear? Now if we want to show the two separate hydrogen atoms, then when the two atoms start approaching, the electrons of each atom, they will start coming under the influence of the nucleus of the other hydrogen atom. Let me show you. See, if this is the Ha and this one is Hb, suppose this is the nucleus. Okay, and the electron of this Ha is here and the electron of Hb is, suppose it is here. Clear? Now what will happen? There will be an opposite attractive forces between the electron of this hydrogen atom and the nucleus of this hydrogen atom. That means one force of attraction will be in this way and another force of attraction will be in this way. That means the nucleus of the A hydrogen atom will attract the B electron and the nucleus of the B hydrogen atom will attract the A electron. Okay, and the repulsive forces will act between this electron and this electron, means between these two. Here there will be a repulsive force, okay, and between these two, means these nuclei, there will be the repulsive forces. So attractive forces, it will occur between the electron Ea and the nucleus of B hydrogen atom, okay, and another attractive force will act between Eb and the nucleus of the A hydrogen atom. Clear? Now repulsive force, it will exist between the two separate electrons, means Ea and Eb, and the other one is between the nucleus of Ha and Hb. Clear? So these are the forces of attraction which will be applicable in this case. Clear? Now we need to know that how these attractive forces bring the two atoms close. See, here the attractive forces will tend to bring the two atoms close, and the repulsive forces, they will tend to push away the two separate atoms. Clear? Now in this case, initially the attractive force is greater than the repulsive force. Naturally the two nucleus will come close, that means two hydrogen atoms will come close to form the hydrogen molecule. Now means after this approaching of the two separate atoms, the atoms go on approaching each other and the potential energy of the system continues to decrease. Clear? Ultimately a state is reached where the attractive forces will balance the repulsive force, means this attractive forces, they will balance the two repulsive forces. Now this state is reached when the atoms are at the critical distance, that is R0. This is the critical distance. Now what is this critical distance? This is the distance between the two separate hydrogen atoms, where means below this distance, or we can say that at a distance greater than the R0, means when the distance is more than R0, the attractive forces will be dominant, and when the distance is smaller than R0, then the repulsive forces will dominant. Clear? So maximum lowering of energy takes place at this R0, that is the critical distance only, and the lowering of the potential energy as a function of internuclear distance, it will be seen in case of the, if we plot it, means let me show you the plot. See, this is the type of plot where we will see that how the change of potential energy is there as the two hydrogen atoms approach each other. Now see, when the hydrogen molecule is there, the potential energy is maximum. Like if we take the example of the means this one, when H2 gets broken to form two hydrogen gaseous atoms. Okay, so initially when it was in the bonded condition, then the potential energy was maximum. Now it was decreasing gradually. Okay, after some time it will reach a value where the means the bond length is, that is the critical distance R0. This, suppose this one is the critical distance R0. Here it is the closest approach of the two separate hydrogen atoms. That means here the two separate hydrogen atoms are in bonded condition. Okay, this is the bonded atoms. Clear? Now what will happen? This is the energy that is provided to break, that is the bond energy we can say, or bond enthalpy. Okay, this much energy has been provided to break this bond. Now gradually this energy will again increase and it will reach a value very close to this one. Clear? So in this situation, or at this condition, here the atoms are approaching, means there it is not bonded but it is in the approaching condition. So we can say it as the approaching atoms. And at this condition, here the two atoms are separate, means it is the approaching one, and here the two atoms are separate. Okay, so these are the separate atoms. Clear? Now if we want to see the atomic orbital concept, then I can show you the exact s orbital overlapping. Let me show you. See, initially the s orbitals are in this way. Okay, that means two separate hydrogen atoms are there where there is no interaction occurring. Okay, so let's take it as the nucleus. These are the nucleus and the electrons are located outside. So these are the two separate atoms where there is no interaction. Okay, now when these two atoms will approach each other, they will come close. Okay, in this way. These are the nucleus. So these are the approaching atoms. That means the interaction starts. Okay, and now after the interaction has been complete or the bonding has been taken place, so in that case we call it as the bonded atoms. Here they have their separate nuclei, but this is the maximum distance. To that extent they can exist, means this distance they have to maintain. Okay, so this is the bonded condition, or these are the bonded atoms, and this is the orbital overlap. Okay, so two s orbitals have been overlapped here. This is the atomic orbital. Clear? The overlapping of the atomic orbitals. Clear? Now another thing that you need to know, that why helium molecule is not formed. You can explain it by yourself only, or you can take the example of the hydrogen atom, how these forces of attraction or the repulsive forces are occurring in case of the helium molecule. It is the inert gas and only 2 electrons are there in the s orbital. So there will be the repulsive force maximum. That means the bonding will not form, the interaction won't take place, and helium molecule won't form. Okay. So in case of the helium molecule, since the energy of the two separate helium atoms is smaller than that of the system when they are close to each other, so they prefer to stay separate and they do not form the helium molecule, He2 molecule. Okay. Now we will learn how the overlapping of atomic orbitals take place and how the formation of simple molecules take place. Let me show you. See, when two atoms approach each other to form a bond, their atomic orbitals simply overlap. And this type of overlap can be, means this overlapping can be of 3 types. One is positive overlap, another is negative overlap, and the third one is the zero overlap. So what is positive overlap? Positive overlap is that case where the overlap of the lobes of same signs take place. So it leads to the attractive interactions. Let me show you. Here you can see that pz orbital is getting overlapped with another pz orbital of the same lobes, means the same the lobes of the same sign, they are getting overlapped, and this type of overlapping is called the positive overlap. Here in case of sp overlap, one p orbital of positive lobe is getting overlapped with the positive lobe of the s orbital, though s orbital has only one type of lobe, we can say. And in case of px also, the two same px orbitals are getting overlapped where the two lobes are facing each other. Okay, and in case of the py orbitals also, the overlapping is the positive overlap. That means this type of overlap, it leads to, or it shows the attractive interactions. Okay, these are the attractive interactions. Now in case of negative overlap, it involves the overlap of the lobes of opposite signs, and it will lead to the repulsive interactions. So here you can see that the lobes of the opposite signs, they are getting overlapped, and this type of overlapping is called the negative overlap. So here it leads to the repulsive interaction. So these are the repulsive interactions. Okay, and the last type is the zero overlap. So in this case, in case of the zero overlap, it implies the inability of any kind of interaction. That means there is no proper overlap. So this shows the inability of formation of any kind of interactions. And let me show you the difference of the overlapping. So if such kind of mismatch is there, that means there is no proper interaction. So that kind of overlapping is called the zero overlap. Clear? So these positive, negative and zero overlap shows that how the atomic orbitals get combined with each other to form the separate types of bond. Generally, due to these overlapping, the covalent bonds are formed. Okay, so now we will know that how the various postulates of orbital concept are there regarding the formation of covalent bonds. So it is said that the covalent bonds are formed by the overlapping of the half-filled atomic orbitals which are present in the valence shell of the combining atoms. That means if the two separate hydrogen atoms get combined to form the hydrogen molecule, then the half-filled atomic orbitals of the two separate hydrogen atoms, they will undergo the overlapping. Okay. Now the next thing is the orbitals which undergo the overlapping, they must have the electrons with opposite spins. And the other concept is that the strength of a covalent bond, it depends upon the extent of overlapping. That means greater the overlapping, more is the energy released, and finally we can say that the covalent bond will be stronger. So these are the postulates which express the formation of covalent bonds using the orbital concept. Now the covalent bonds can be classified into two different categories depending on the type of overlapping. So the type of overlapping will tell us the nature of covalent bond, and the two separate types of covalent bonds are the sigma bond and pi bond. So let's discuss the sigma bond first. So in case of the sigma bond, there is the axial overlap. Axial overlapping of the half-filled, means the two separate half-filled atomic orbitals, they overlap axially. Okay, so this type of bond is also called the head-on overlap. So sigma bond can be of three different types. The axial overlapping can occur between s orbital and p orbitals. So the three different types of overlapping are the SS type, SP type and PP type. Okay, let me show you. So here you can see that when two half-filled atomic orbitals, means the s orbitals, they overlap in this way, this is called the SS sigma bond. When one s orbital gets overlapped axially with the other p orbital, it is called the SP overlap. And this type of axial overlapping between two separate p orbitals is called the PP overlap, and the sigma bond consists of only a single bond. Clear? Now, as I said that the strength of a covalent bond depends upon the extent of overlapping. So as the p orbitals allow the overlap to a greater extent as compared to the SP overlap or the SS overlap, so the strength of these type of overlaps follows the order that PP overlap is the strongest one, then SP overlap and then SS overlap. Clear? This is the order of strength of sigma bond. Clear? Now the next type is the pi bond. Pi bond is formed by the lateral overlap or the sidewise overlap of the atomic orbitals. So the sidewise overlap or the lateral overlap takes place in this way. Okay, we cannot include the orbitals in this way, because if the two separate pz orbitals get overlapped, then this will give rise to the formation of the sigma bond, because there is the head-on collision or head-on overlap. Okay, but here when the two separate p x orbitals or p y orbitals are getting overlapped, they are overlapping laterally, or the sideways overlap is there. So this type of bond is called, this gives rise to the formation of pi bond, not this one. This is the sigma bond. Clear? Now you need to keep in mind that sigma bond is stronger than pi bond. Okay, because the overlapping of the atomic orbitals can take place to a greater extent during the formation of sigma bond. Okay, whereas the overlapping of the orbitals occur to a smaller extent during the formation of the pi bonds. So sigma bond is stronger than pi bond. Another thing that you need to keep it in mind, that pi bond between two atoms is formed only in addition to a sigma bond. That means to exist a pi bond, there must exist a sigma bond. Let me show you how. See, for the formation of ethene, here two carbon atoms are connected with each other using a double bond. That means one sigma bond and one pi bond. So look at here. For the pz axis, there is one overlap of the pz orbitals of the two separate carbon atoms, right? So this orbital overlap gives rise to the formation of one sigma bond between the two separate p orbitals of carbon atoms. Now there is one sideways overlap for the py. This one is pz, this one is py, and this one is px. For this one it is py, px and pz. So between the py orbitals there is one overlap, and this atomic orbital, means this sideways overlap of the two py orbitals, will give rise to the formation of one pi bond. Clear? So among these two double bonds, one sigma bond is there and one pi bond is there. Now why cannot the pi bond exist alone? Because there always will be one pz orbital which will form, means which will undergo the head-on overlap and give rise to the sigma bond. Okay, so along with the pi orbital, always a sigma bond exists. Now for the rest of the hydrogen atoms, one atom will get attached here for the formation of sp overlap, another will get attached here, means one hydrogen atom, another hydrogen atom, and here we can show it in this way, one hydrogen atom, another hydrogen atom. Okay, so this is the formation of ethene. In this way the overlap takes place. Clear? So this is all about the orbital concept of the atomic, means the overlapping of the atomic orbitals. Clear? And you will get the comparison of the sigma and pi bonds in your textbook. Please go through it. So this is all about the overlapping of the atomic orbitals and the formation of the various covalent compounds. Clear? In the next class we will discuss the other bonding parameters and the concept of hybridization. So this is all about today's class.